All right, let's see here. We've got to talk about some systems of equations. So we are moving on to Unit 5, and again, that is systems of equations. And we're going to first start by doing a little bit of a review. So you are more than welcome to fast forward. I'll tell you where the new stuff starts, but I'm going to review systems of equations so that we are all on the same page. So, first of all, what is a system of equations? So, hopefully we all know the answer to that, but if you don't, it's just any collection of equations with a common set of unknowns or variables. So generally the ones that you've seen, and you've learned about these when you were babies, so you did this probably in middle school, and we usually start you off learning systems of equations with just two variables, x and y, or some application where they're going to be assigned different values, and usually those systems are linear. You may have seen some that went outside the linear system, maybe some quadratics or whatever. But the whole point of a system of equations is you're searching for the solutions for these variables that satisfy every equation in the system. So I'm just going to start off by giving you an easy one, and hopefully you're familiar with the notation here, but this is just a grouping symbol, curly bracket, that's saying I'm going to have two equations in this system. So the first one is x plus y equals 2. So here are my two unknowns. The combination of these two when I add them together equals 2. But also, if I multiply 2 times x and subtract 3 times y, it should also equal 9. So these two equations are working together in one system. So if we solve for x, it has to work for both. So ways that you learn to solve systems of equations, you learn substitution, elimination, and graphing. So we're going to touch on all three of those, but before we do that, I just want to talk about what if I gave you a coordinate, and that coordinate, the first one will be 1, 1. And I want to know, is this a solution? Does this solve this system? So where x is 1 and y is 1. So we can go ahead and just do a little plugging and chugging. So if I substituted it here, I have 1 plus 1, and yes, that does equal 2. So this solution does solve the first equation in the system. In order to be a solution to the system, it has to work in the second equation. Is 2 times 1, minus 3 times 1, does that equal 9? And that is definitely not true. So this is not true. Meaning, this does not solve the system. So we could try a different one. What if I gave you a different coordinate, 3, negative 1? Does this solve the system? And we would do the same thing. So I'm plugging and chugging. Does 3 plus negative 1, does that equal 2? Yes. Does 2 times 3 minus 3 times negative 1, is that equal to 9? So is 6 plus 3 equal to 9? Yes. So this is a solution to the first given system. So this means if we were to graph this system, these two lines would meet at this coordinate on the coordinate plane. So when you're solving by graphing, you're looking for where two different lines intersect. Now, before we would be able to graph these, of course, we would have to put them in slope-intercept form. So those are that's the easiest way to graph a linear system. So I can show you how to do that for these two. I'm going to just go ahead and do it on my calculator, but I've got to get it off polar mode. Okay, so this first equation, x plus y, equals 2. So it needs to be in slope-intercept form. So y equals mx plus b. So I'm solving for y, so I would subtract x. So I would have negative x plus 2. So y equals negative x plus 2. The second one's a little bit more complicated, so I'm moving 2x to the other side. So I would have negative 3y equals negative 2x plus 9, and I'm just moving the 2x here because I want it to be in this form, and then I need to divide everything by 3. So negative 2x divided by negative 3, 2/3 x. 9 divided by negative 3 is negative 3. So if I go ahead and type that in, plus 9. And if we graph this, we should see the solution. What did I do wrong? Oh, duh. Minus 3. Why? Much better. Okay, so now we can find the point of intersection. So remember, we're not just using our arrows to do that. We're making our calculator actually calculate it for us. So we go to, I did second trace, the calculate menu, and you can see intersect is one of the choices. Look at the top, it says is the little cursor, is the blinker, on the first equation, and of course it is, that's the first one we entered. So if that's true, all you do is hit enter, and then it moves and says, am I on the second equation? See up here, that is the second equation, finally the right one that I typed in. Go ahead and hit enter. So we talked about guessing. You can go ahead and guess if you really, really want to, but remember we said if you make a guess that is way off track, your calculator kind of poops its pants and shuts down. So just hit enter instead of guessing, and then it gives you 3, -1. So we can see that, in fact, even though I gave you this at the beginning, you're absolutely able to solve a system using graphing. If it's linear, it has to be in slope-intercept form before you can put it in your calculator. All right, so easy peasy. Now let's talk about what is it called when a system has a solution. So when we look at the system that has a solution here, this 3, -1, a system with a solution is called consistent. It's a consistent system. Now, there's a difference in having a solution. It can even have multiple solutions to be called consistent, but something changes when it has an infinite number of solutions. So it is possible to have an infinite number of solutions, and I'm going to show you an example of that soon. But if it has an infinite number of solutions, it's called a coincident system. And that word may seem familiar to you, and it may make more sense whenever I show you an example in a second. It's also possible, though, that a system does not have any solutions. And I'll show you an example of one of those as well. So if there are no solutions, if the solution set is, if the system is not solvable, then it's called inconsistent. So these are the 3 different types of systems that we have based on the number of solutions. So no solutions, inconsistent. An infinite number of solutions, coincident. And then 1 or more solutions to the set, and they have to be like a finite number of coordinates like this, then it's called a consistent set. All right, so let's go back to this system and talk about, so we talked about how to do graphing. Let's talk about substitution and elimination. So I'm going to do that for you guys. Let's do it on here. Why not? So we've got our grouping symbol, x plus y equals 2. 2x minus 3y equals 9. So if we want to use the substitution method, what we're doing is we pick one of the equations, and it doesn't matter which one. Sometimes one is easier than others, but you pick one of the equations and solve for one of the variables. And then once you do that, you substitute it into one of the other equations in the system. So let's look at equation 1. Equation 1, I could solve for x by subtracting y to the other side. So x would be 2 minus y. X equals 2 minus y. So because I solved for x, I'm going to substitute it in to the second equation. 2 times x, which is now 2 minus y, minus 3y, has to equal 9. So I can distribute 4 minus 2y minus 3y equals 9. I'm going to move my 4 over and combine my like terms. Negative 5y equals 5, and y is equal to -1, which we saw a second ago that was true. That was the y coordinate. So how do we find the x coordinate? We substitute this back into one of the original equations to solve for x. If you look here, when we solved for x, it's already ready for us to just throw this guy in. So if we throw negative 1 in, we have 2 minus negative 1, or 2 plus 1, and we see that x is equal to 3. So get in the habit of writing your solutions in a coordinate form, because that's truly what it means. It's showing where the solutions are, where the lines would intersect. All right, so what about the elimination method? So the elimination method is where it's a little bit, it could be more complicated. Some people view it as more complicated, but you're trying to eliminate one of the variables from within the system. So like if I look at the coefficients here, these are both positive, but these are opposite signs. So my preference is to manipulate the ones that have opposite signs, because I'm trying to eliminate by making the coefficients equal 0 when I add or subtract these equations together. So right now I have negative 3y and positive 1y. So what I'm allowed to do is multiply one of the equations in a system by some constant that's not equal to 0. So I just have to be consistent and multiply the entire equation by that constant. So what if I took this whole equation and multiplied it by 3? What does it become? So this would now be a system with 3x plus 3y equals 6. So I gave 3 to every single term in that equation. Now, the second equation I'm going to leave alone. So I'm allowed to do this because I've kept something consistent. All I've done is tripled this equation. So I haven't changed any of the values. I've just made it larger. All right, so now you can see that we have the y variables have the same number but opposite signs. So if we were to add these two equations together, so we're adding the equations together. So we're saying equation 1 plus equation 2. So we're combining like terms. So 3x plus 2x is 5x. Negative 3y minus 3y, that's 0, equals 6 plus 9, which is 15. So now we have a much more simple equation to solve. X is equal to 3. And just like before, once we have one of the variables, we need to go plug it back in to solve for the other. So I'm going to use this first equation. Before I multiplied by 3, I always go back to an original equation. So 3 plus y has to equal 2. And that's how we can see that, again, y is equal to negative 1, which still gives us the 3, negative 1 as a solution. All right, so that should be a good reminder of the 3 different types of solution methods for solving a system of equations. So what I want to talk about now is ones that are a little bit different. So by that I mean we're going to find ones that fit those other scenarios where it was a coincident or an inconsistent system. So let's talk about how to do those. Let's see. Yeah. All right, so I'm just going to keep working on this. So here's a new system. So 3 halves x minus 3y equals negative 9. And x minus 2y equals 4. So I'm going to start by the substitution method. And I am going to decide which of the two equations is easiest to solve for one of the variables. And when I look at this, I see the second equation is easiest to solve for x. X would be 2y plus 4, right? X is, I just moved the 2y. So now that I have a solution for x, I'm going to plug it in up here. So it's 3 halves times 2y plus 4, because it's 3 halves of x, minus 3y equals negative 9. And I'm going to distribute 3 halves of 2, 3 halves of 2y, plus 3 halves of 4, Alright, so let's take a look at what's happening here. I'm going to move the 6 to the other side because it's alike, right? These are my two constants. But when I combine the 3y, positive 3y and negative 3y, what I end up getting is 0 equals negative 15. And I don't know about you, but that is definitely not true, right? Definitely not true. So this is a big fat nope. So what does that mean? Did we do something wrong? And, honestly, sometimes the answer to that is yes, but this is an example of one where this is an inconsistent system. And it's inconsistent because this statement is not true, nor will it ever be true. And let's say I didn't even move the 6 over. What if I just saw here that these cancel, and I would have 6 equals negative 9? That's still, 6 does not equal negative 9. That's still not true, and there's no way to make it true. So this is an inconsistent system. So maybe you're asking, well, what if we did a different way of solving? Like Ms. Schaefer, I really like elimination. So what if we tried elimination? So let's try that here. So if I wanted to eliminate one of the variables from the system, my preference, again, is to find variables that have opposite signs. And unfortunately, in this system, we don't. We have a positive, positive, and a negative, negative. So that's okay. It just means when we go to multiply one of our equations, we have to multiply it by a negative. So it doesn't really matter which one you do. I'm going to go ahead and take this second equation. I'm going to take the second equation, and I'm going to multiply this guy and multiply him by negative 3/2. And to me, that's just easier because it has a coefficient of 1. In order to eliminate the y's, I would have to multiply them both by something. Whatever. Maybe you don't want to multiply by a fraction, and that seems better to you. It's up to you. All right, so first equation, 3/2 x minus 3y equals negative 9. He doesn't change. Second equation, I'm multiplying by negative 3/2. So negative 3/2 x, negative 3/2 times negative 2 is a positive 3y equals 4 times negative 3/2, again, negative 6. And if we add these two equations together, so I'm combining the two equations to make a more simplified equation, negative 3/2 x minus 3/2 x, so we're eliminating x, which is what our original goal was, but we also end up eliminating y. And again, we're seeing 0 has to equal negative 15. This is not true. It will never be true because this is an inconsistent system. It ain't gonna happen. So that means there are no solutions. So imagine then what the graph would look like if I were to graph these two equations the same way we did on the previous example. What does it mean if two lines don't meet? What's it called when we have two equations or two lines that will never ever meet? So when you have an inconsistent linear system, it's because the lines are parallel lines. We have parallel lines. So let's see what happens when we take these two equations and let's solve them for y. So we put them in their y equals mx plus b form. And if two lines are parallel, what do you know? What do they look like when they're in mx plus b form? Parallel lines have the exact same slope, or the exact same m value, right? So let's look up here. If I solve the first equation for y, the first thing I'm going to do is move this guy over. So I have negative 3y equals negative 3/2 x minus 9, dividing by negative 3 or multiplying by negative 1/3. Y equals, I'm multiplying by negative 1/3. So 1/3 1/2 x multiply by negative 1/3 plus 3. And I'm going to do the same thing to this equation. So I'm moving the x over. So here's equation 1. Equation 2, I would have negative 2y equals negative x plus 4. I'm dividing by negative 2, or multiplying by negative 1/2. Y equals 1/2 of x, multiplying by negative 1/2, plus is this positive 4? Yeah, okay. Minus 2. Gotta get a different marker. These are awful. Okay, so here are two equations. They have the exact same slope, but do you see how they have different y-intercepts? What would it mean if they had the same slope and the same y-intercept? Wouldn't that imply that they're the exact same line? And if they're the exact same line, wouldn't that then come over and be an example of an infinite solution? So if we have coincident a coincident system that has infinite solutions, that's going to be where the lines lie right on top of each other. So these are parallel lines. They're moving with the same slope, but they have different y-intercepts. So let's look and see what they would look like on our handy-dandy. So we had 1/2 x plus 3 and 1/2 x minus 2. So we've got parallel lines. Parallel lines that never touch, hence the system is inconsistent because you have to have an intersection in order to have a solution. So we don't have a solution here. Inconsistent. Alright, let's see what else I had for you guys. I can show you an example of one that will be coincident. So 3x plus 4y equals 12, and 2y equals 6 minus 3/2 x. So first thing when you see a system like this that's not lined up nicely, I would go ahead and do that, meaning the x's should be lined up in columns, the y should be in columns, and so should the constants on the other side of the equals, is normally where we place them. So that just means I'm going to take this over to this side. So this system I'm working with would be 3x plus 4y equals 12, and then 3/2 x, just moving this guy over, plus 2y equals 6. So this makes me happy because now he looks better. He looks like he's supposed to look. Alright, so, I don't know, it doesn't matter which way, algebraic way we choose to solve this, so I'm going to go ahead and eliminate, because that's my preferred method. So I'm going to take this, and I'm going to multiply it times -2. So if I change this to a -4 and then add those two, that's how I'm going to get rid of, eliminate the y's, and then solve for x and go from there. So I have 3x plus 4y equals 12. The second equation becomes -3x minus 4y equals -12. So now when I go to add them, this is one of those weird ones, so these 3x minus 3x, that's 0. 4y minus 4y is 0, and then I have 12 minus 12, which is also 0. So the difference here is we have our final equation, when we've manipulated everything, is we have 0 equals 0, and this is true. Yet all of the variables have canceled out. So we can't solve for x or y, but we have a situation where the equation is balanced. So this is a coincident system. It actually has an infinite number of solutions. When this happens, it means if you pick any value of x, you can figure out what the y value is. Always. There will always be a solution. So let me show you graphically what this is going to mean. So if they're coincident, we know that the lines should lie on top of each other. They have an infinite number of solutions. So let's go back up to our original, and we just want to solve them both for mx plus b. So the first equation, 4y equals -3x plus 12. The second equation, so I'm just going to put it back to what it was here, but I'm just going to rearrange it because I want my slope to come first, plus 6. Alright, so final step would be, in both of these cases, to this one I'm dividing by 4 and multiplying by 1/4. So y equals -3/4 x plus 3. Okay, and over here I'm dividing by 2 and multiplying by 1/2. So -3/2 times 1/2 is -3/4 x. See how they have the same slope? But now when I divide 6 by 2, I'm getting a same y-intercept. So if I were to graph these both, I'm graphing the exact same equation, so what do you expect would happen? You would only see one line. So there's an infinite number of solutions, and it would just be any points that satisfy this line. So you can always plug in an x and get out a y, because it's going to happen for both of them. So, easy peasy. Alright, so what if I gave you something a little bit more difficult, just in terms of, I don't know, sometimes you'll just be asked to use technology to solve a system, so I created one of those. I don't know, so solve using your calculator or technology. So you can use Desmos, you can use your calculator. So 2y equals x minus 18, and y equals 0.4x plus 1. So whenever you're using your calculator, it should always be in slope-intercept form. So y equals mx plus b. If it's a linear system, and that's generally what we're focusing on, that's why I keep saying mx plus b, but systems can be different types of polynomials or different types of functions. So this one's already good for us, so I can put that in my calculator, but this one isn't. So I just need to take him into mx plus b, which is as easy as dividing everything by 2. So y equals 1/2 x minus 9. So I can tell that these have different slopes, and that means that this system is not going to be coincident or inconsistent. So both of those times is when the slopes, because it was a linear system, their slopes had to be the same, and then with that added part of having the same y-intercept if it was going to be the exact same line. Oh, okay, so 1/2 x minus 9 and 0.4x plus 1. Alright, so this one's interesting because if we just look at this window that our standard window is, it almost looks like these graphs are parallel, and it doesn't seem like these graphs are touching because of this small window that we're using. So what we need to figure out is where these two graphs are intersecting. We need to use our calculator. We're using technology. So I don't want you to solve this one by hand. I want you to be able to do this on a calculator as well. So what it means is I'm standing too close to the function, so I want to step back. So I'm going to zoom out. So when I do zoom out, you have to hit enter. It's focusing on the origin, and it's moving away from the origin. And most of your calculators have a factor of 4 zoom out. Now that we've zoomed out, you can see these lines aren't parallel, and it looks like they're getting closer and closer to each other up here. So let's try to zoom out one more time. And we can still see there's no intersection on this window, but I can definitely now tell that they're going to touch each other up here. So here's where I could keep zooming out, but it's going to be a little bit weird. If you see what's happening to the x-axis, so I don't necessarily need my x-axis to change, I just need my y-axis to change because it's happening up here somewhere. So I'm going to go to my window, and now I'm going to go change my y maximum. I'm going to actually change this to 0. And I don't know how far up. I'm going to start with, let's start with 150. Let's see what happens. So now we can see that these are touching. And you could play with your window a little bit more. What if I just did 0 to 100? So now I might have gone, I'll just set this one to 150 as well. So we can definitely see that they're touching. They're touching in one place. It's linear, so they're either touching once, never, or always. So we can see where they're touching. So remember how to call up the intersection. Do not use your arrows. They're not precise. So second calc, second trace, intersect, first equation, yes. Second equation, yes. Guess, probably not, right? And then it tells us where the intersection is. So we're looking at the coordinate 141. And you can always plug this in and make sure that it works. Just to make sure that you did this step correctly and that you typed it into your calculator correctly. So how do we check it? Exactly the way we did at the beginning of this video. You're just plugging the point in and showing a balance. Okay, so hopefully that was a nice little review. I'm going to write down our time. So let's now talk about what happens when we have a system of equations in more than 2 variables. So we're kind of traveling away from just having 2 variable systems, and we're going to talk about 3 variable systems. And when we solve 3 variable systems of equations, it's not just x and y, it's x, y, and z, or it's a, b, and c, or it's q, r, and s. It doesn't matter, but it's 3 unknown variables. And I'm going to show you an example of one, and then we're going to talk about methods of solving these. So, of course, we're increasing the number of variables, which means we are going to increase the complexity a little bit. I'm going to use the example that I've already done that I know is going to be pretty. All right. So we have x, y, and z here. And I'm starting off a little bit easier, but you can see we have 3 equations because we have 3 variables. Now, that's not standard. You can have 2 equations and 3 variables, and we'll talk about those as we progress. So when we solve a system with 3 variables, 3 equations, 3 variables, we use something called Gaussian elimination. And it's named after a mathematician, Carl Friedrich Gauss, and he actually developed it in the 1800s, and he used it to analyze the orbit of an asteroid. So pretty cool to think of somebody doing that back in the 1800s without all the fancy technology that we have now. You know, but per usual, this guy who has this named after him wasn't the first person who actually created this process. It's actually been documented in Chinese literature going back 2,000 years. So it's been around for a while. But essentially what Gaussian elimination is back substituting. And, substituting? Yeah, it works. All right, so it can be really simple, like this example, or it can be a little bit more complicated. So I'm going to start you off easy, and then we're going to work backwards. But it's back substituting, meaning if you can get an equation in the 3rd spot, or really in the 2nd spot, wherever, but that's just with one of the 3 variables, it's easy to solve, right? We can solve this 3rd equation very simply to get what z is. Z is equal to 4. And once we have z, now we can go backwards, and we can go to the 2nd equation, substitute that in, so go backwards to substitute it in order to find out what y is. Then I'd have z, I'll have y, and then I can go backwards to get x. So I have z, so now we're taking z into the 2nd equation, so we would have 5y minus 2 times 4 has to equal 2. So 5y minus 8 equals 2, 5y equals 10. So now we know y is equal to 2. And if I know x and y, I'm going to go back to the 1st equation. I have 3x plus 2 times y minus z has to equal negative 3. So 3x plus 4 minus 4 has to equal negative 3. 3x has to equal negative 3, or x is equal to negative 1. Now, when we solve a system with 3 variables, we also should write it as a coordinate. So this is a 3-dimensional coordinate. And it's just written the same way, but it's in the order x, y, and then z. It's called an ordered triple, and these 3 numbers must satisfy all 3 equations in the system. So again, this was an easy one, but they do get a little more complicated, so we're going to talk about a more complicated one now. And before we do that, I'm going to give you a few rules for Gaussian elimination. So, we call these the 3 elementary operations. Gaussian elimination. The first one. You are allowed, and a lot of these are going to sound very familiar, but you are allowed to multiply an entire equation, or both sides of an equation is the mathematical way of saying that. Both sides of any equation in the system by any non-zero constant. So non-zero can't be a 0. Constant, it can only be a number, no variables. We're not multiplying by variables, but any non-zero constant. So it can be positive, it can be negative. Should sound familiar. The second elementary operation. You are allowed to interchange or swap equations. You can interchange the order or swap the order of any two equations in the system. And this could be useful just for organization purposes. And finally, you're allowed to add any multiple of one equation to another equation in the system. So these rules are very similar to the rules that you use with two-equation system. So the only thing that's different maybe is interchanging the order, right? Because now we have three equations, so it may be better to group equation 1 and 3 together instead of 1 and 2. So let's look at an example. I did a pretty one. So x plus 2y plus z equals 3. 2x plus y plus z equals 16. X plus y plus 2z equals 9. All right, so remember what our focus is. Our focus is on elimination. And there's always going to be multiple ways to go about doing these problems. So I'm going to show you how my brain worked on this problem, and probably in the middle of it, I'll have another idea and screw myself up, but that's just who I am, and you guys are used to it. So I'm going to use some notation here, and we're going to clean up the notation as we start learning this. So I'm going to introduce some of the standard ways that we solve this. So the first thing I'm going to do, my focus is going to be on eliminating x from the second two equations. So if you look at the previous example that we did, it was missing x from both of these equations. And that's kind of one of the goals. You want to try to do that. So let's eliminate x from those two equations. So the first thing I'm going to do is I'm going to, I already forgot. What did I do first? I think I took equation 1. So I'm just going to make a little note of what I'm doing. So I took equation 1, I subtracted equation 3 from it, because I'm allowed to change the order, meaning I can skip around if I want to. So I'm taking equation 1, I'm subtracting equation 3 from it, so I hope you see why I'm doing that. But what I'm going to do with that, and this is kind of the new part, is I'm replacing the old equation 3 with that new answer. So when I do this step, the system becomes, I'm going to replace equation 3 with this thing. So equation 1 minus equation 2, x minus x, the x's go away. 2y minus y is just 1y. Z minus 2z is negative z. And 3 minus 9 is negative 6. So this is the only change I've made right now. So I'm going to rewrite everything else in the system exactly the same way. So this process takes a little bit of time. So here was the first thing I did. So the next thing I want to do, like I was saying a second ago, is I want to eliminate x from this equation as well. So I'm going to go back to equation 1. What can I do to equation 1 this time to eliminate this one? So this next thing I'm going to do, so here's just a log of what I'm doing, is I'm going to say negative 2 times equation 1, negative 2 times equation 1 plus equation 2. And I'm going to rewrite that answer in equation 2. So I'm going to come down below it now. So let's focus on equation 2. So negative 2 times equation 1 plus this thing. So negative 2 times x plus 2x, x's are gone. Negative 2 times 2y plus 1y, negative 3y. Negative 2 times z plus z is negative z. Negative 2 times 3 plus 16, so negative 6 plus 16 is 10. So that's the only thing I've changed, meaning I'm going to keep my first equation the way it was. and my third equation that I've already changed to be this. So I've done what I accomplished to do first, is I've eliminated x from the two equations below it. So if we go back to our model equation, what else do you notice? So we have the second equation here that has y and z, it's missing x, and then what do we see in this third equation? So we have only one variable in the third equation. So let's see if we can come up with a way to do that. Is there a way to get only one variable in the third equation? And hopefully you see that there is. So the third thing I'm going to do, so even though the last equation had it was solved for z, the focus is to have just one variable in the third equation. It doesn't matter which one it is. So you want all three variables, only two of the variables, and just you get one of the variables. And it's kind of, we call it triangular form. So is there a way to get only one variable? And if you want it to be z, you can make it z, but I think it'd be actually easier to eliminate the z's. And how are we going to eliminate the z's? So what if I said equation 2 minus equation 3? So I'm doing that because I'd have -1 minus -1, and that would be -1 plus 1 or 0, right? And I'm going to replace that old equation 3 with this new equation 3. All right, let's see. So let's focus on equation 3. So I have equation 2, -3y minus y. -3y minus y is -4y. Negative z minus negative z, because I'm subtracting. That's 0. I have 10 minus -6. That's 16. So I've done this, so now everything else, I just rewrite it, because I haven't changed it on this step. And so now that I've got this in triangular form, 3, 2, 1, right, it's very easy to solve. The last equation, -4y equals 16, y equals -4. Once I have y, I go back up. So to solve for z, -3 times -4 minus z equals 10. So z equals 2. Now I have y and z. I'm going back up to x. So I'm substituting y and z in, and I get x is equal to 9. So I write my answer as an ordered triple. So a coordinate in order. So x has to come first. Not what I solve for first. X comes first, then y, then z. Here is our answer. So Gaussian elimination takes some time. It is an organized way to solve a system of equations. Otherwise, it can get a little bit crazy. So I'm going to do one more, maybe two more. Let's do one more. This video is already long. All right. Let's see if we can do it on this without running out of space. All right. So, I'm just trying to pick which one I want to do last. This one looks good. Okay. We've got 4x minus 3y plus 2z equals 40. 5x minus 9y minus 7. Okay. And I'm just making it first. 7z equals 47. So it's plus 9y minus 7z equals 47. 9x plus 8y minus 3z equals 97. All right. So this one's, I don't know, I thought this one was kind of fun and different. So it's a little bit more difficult. So this one I think would be kind of tough. So take your time, rewind, stop, whatever you need to do. So the first thing I'm going to do is, let's do equation 2 minus equation 1, and I'm going to replace equation 1 with that. So the reason I'm doing that first is so that I have a coefficient of 1 here. It's just going to make things easier as I go to start eliminating x's below it. Okay, so here's our new system. So I'm replacing equation 1 with this minus this. So this would be x 9 minus negative 3 plus 12y, negative 7 minus 2, and 47 minus 40. Okay, and then I didn't change anything else, so I'm just going to rewrite 7z, rewrite the other two equations. Okay, and so now my goal is to eliminate the x's here. So I'm actually going to do that in two steps in one. So I know to eliminate this guy, it would be negative 5 times equation 1 plus equation 2. That's what I'm going to write in equation 2. And then to eliminate this guy, it would be negative 9 times equation 1 plus equation 3. That's going to be my new equation 3. So I'm just, in 2 steps, I'm just going to do both of my x eliminations. All right, so the new system, I'm not changing equation 1. See, these are the only 2 new ones. So negative 5 times this plus equation 2 is what I'm going to write now. So negative 5 times 1 plus 5. X's go away. Negative 5 times 12 plus 9. So negative 5 times 12 plus 9 would be negative 51y. Negative 5 times negative 9 plus negative 7 plus 38z. Negative 5 times 7 plus 47. So negative 5 times 7 plus 47 is 12. So now I'm going to do equation 3. So I'm going to rewrite equation 3 by negative 9 times this plus equation 3. So that's what I'm going to write. So negative 9x plus 9x, gone. Negative 9 times 12 plus 8, negative 100y. Negative 9 times negative 9 plus, where am I, negative 3, 78z. Negative 9 times 7 plus 97 is 34. So you can use your calculator to check those if you are not a good mental mather. Alright, so this next step is kind of unconventional, but what I'm noticing is I've got some really big coefficients down here, and what I can do, can't do anything to this one right now. I was checking to see if everything's divisible by 3, it's not. But everything down here is divisible by 2, so I'm just going to make my life easier, replace equation 3. It's 1/2 of itself. So all I'm doing is dividing all of the coefficients by 2 or multiplying by 1/2. Remember, that was one of my rules that I'm allowed to do. And this is a prime example of why we could use it. It's not really the most optimum way, but it's just to make the coefficients easier for us. So negative 100 times 1/2, negative 50. 78 times 1/2, 39. 34 times 1/2 is 17. And now what I'm seeing is this was helpful to me not only because I had these smaller coefficients, but now it's easy to see how these are only 1 unit apart from each other, these 2 coefficients are. So what if our next step, we said the new equation, this is equation 2, the new equation 2, I don't want to change the way that I'm writing these for you guys. Equation 2 minus equation 3 is going to be my new equation 2. And what I'm doing to this is kind of very similar to the first step, is just giving one of the equations a coefficient of 1. So my equation 2 is the only thing that's changing, and I'm saying this guy minus this guy. So negative 51 minus negative 50. So negative 51 minus negative 50. So negative 51 plus 50 is negative y. 38 minus 39 is negative z. And 12 minus 17 is negative 5. So I'm going to keep equation 1. I'm going to keep equation 3. So the last step to get this in triangular form is to eliminate one of the variables from the final equation. So again, the reason I did this previous step was to give these coefficients of 1. It just makes it easier to do elimination below it. So I'm going to say negative 50 times equation 2, because I need to change the sign, plus equation 3 will be my new equation 3, because I'm trying to eliminate in equation 3. So I'm running out of room. So I'm going to try to squeeze it right here. X plus 12y minus 9z equals 7. Negative y minus z equals negative 5. So now negative 50 times negative 1 minus 50. So y's are gone. So I'm going to do the same thing. Negative 50 times negative 1 plus 39. So that would be 89z equals 267. So this is what we're looking for, is one variable in the final equation. So now I can solve for z just by using division, right? So 267 divided by 89 is 3. Now, it's okay if it was a fraction. It's very normal for these to be fractional answers, so don't poop your pants if that happens. Once I have a z, I substitute back. Negative y minus 3 has to equal negative 5, meaning y is equal to 2. And now that I have a y and a z, I go back up here to solve for x, and x ends up being 10. So the solution to this system is 10, 2, 3. This is my ordered triple. So x is 10, y is 2, and z is 3. All right, children, that is it for systems of equations. If you hate Gaussian elimination, then you're going to love matrices. So matrices are used to help us with this process. So that will be in the next video, and I will see you then. Adios.